Hi. Today we're going to look at a double integral that if you decide to use a Jacobian, things get maybe a little bit easier. So take a look at this one here. So we have the double integral of e to the x plus y divided by x minus y. All of that is the exponent dA and over region R. And R is equal to the region defined by um, the trapezoid, and the trapezoid has vertices of 1, 0, 2, 0. Oops, sorry about that. And then also 0, -2, and 0, -1. Okay, so it might be worth just to get a look at this trapezoid right away and then see. Maybe we'll just use rectangular coordinates. Like, why even bother using a Jacobian? So and which means changing variables. Like, why get involved with that? So your axes look like this. If we graph those 4 points, we've got 1, 0, and 2, 0. So those are probably here. Here's 1, here's 2. And then the other points we have are 0, -2, and 0, -1. So here we go. Here's -1. Here's -2. All right, so you can see that is some kind of trapezoid. We know that these sides are parallel because both of those sides have slope equal to 1, so this is definitely a trapezoid. Uh, However, we know that if we were going to try and do the integral, the double integral over this region, we would have to break it into two pieces. So let's say we're going to do the double integral, and we're going to do dy first and dx second. Then you would have to split this region here, and this would be one of your integrals, and this would be another, right? So you'd have a double integral, and at least in the first case, you would have x going from 0 to 1. This would be the integral for region 1. And then be another double integral where x would go from 1 to 2, supposing again we're doing dy dx, and this would be region 2. Now you'll notice in both cases I left off what y would vary between. So let's use some of my colors here. So like in this case, for the type 1 integral, then you can tell that line that, for example, we go from this lower line to this upper line here. So we could get those equations pretty easily. The bottom one is x minus 2, and the top one is x minus 1. And then in this other one here, you might say, well, okay, so that's going to go from, y is going to vary from x minus 2 up to 0 because y is 0 all along the top of that boundary. Then you have to add these two integrals together, and maybe that's not so bad in terms of region of integration. One thing that isn't good, though, is how do you integrate that, for example, with, say, respect to y first? If y is the variable, how do you do it? Uh, so that becomes a little bit tricky. So a change in variables here works pretty nicely. So the question is, what do you use for a change of variables? It's not immediately obvious, but if you look at the numerator and the denominator here, then here's a little trick that's cute that works pretty nicely. So I'm going to let u equal x plus y, and we're going to let v equal x minus y. And it turns out that this is a pretty slick um, way to do things, and it makes the region of integration easier, and it makes the actual integral easier to do. So let's take a look at that. So let's think a little bit about how we're going to find out what this region looks like, this this trapezoidal region, this yellow thing looks like after performing this transformation. So if you think about our prior videos about the Jacobian, then we always had this transformation t where x equaled some function of u and v, and y also equaled a function of u and v. And so I'd like to do the same thing here. Um, we just need to be a little bit careful because if you look at our transformation, it's actually sort of the inverse. We have what u equals as a function of x and y, what v is a function of x and y. But we really want it the other way. So we want to have something that says u equals and v equals. So let's do that. So u equals x plus y and v equals x minus y. The question is, what can we do to get these? So here's a fun little trick. Let's say you take these two things and you add them. So you'd have u plus v equals 2x. So then that means x equals 1/2 of u plus v. And so that's clever algebra, but it's not difficult actually. Let's do this again. Let's take these two things, but let's subtract them. Suppose you did u minus v. And if you did that, you would get actually the x's cancel. You get y minus negative y. So you actually get positive 2y. And then you get something that looks very familiar. So, or just like the other one, here you go. U minus v. Okay, so that's pretty handy. So you're actually ready now to do a couple of things. One, we might as well get that Jacobian out of the way while we can. So our Jacobian matrix, I'm going to call it J, is going to be this one, the determinant of partial x, partial u, partial x, partial v, and then I'll have partial y, partial u, and then partial y, partial v. Okay, so if we find all our partial derivatives, are actually pretty nice because the partial derivative of this thing, for example, with respect to u is just 1/2. With respect to v is also 1/2. And then for the second piece, this guy, the partial derivative with respect to y of y with respect to u would be positive 1/2, but with respect to v would be negative 1/2. And now you're ready to do your determinant. So in case you forgot, you do this times this minus that times that. So it looks like you're going to get negative 1/4 minus 1/4, which is negative 1/2. We take the absolute value of this, so we get positive 1/2. Okay, so we're getting there. We know that our double integral now is going to be the double integral of e to the u divided by v. Then we're going to have a 1/2 here because that's the value of the Jacobian, and maybe we'll do the integral du dv. We'll consider the order in a minute. But first we need limits of integration. So let's do a little bit of algebra to look at those things. So let's redraw our original region of integration. So here it is. It has 4 sides. This is 1, 2, -1, -2. And then we also found out that the transformation was x equals 1/2 of u plus v, while y equals 1/2 of u minus v. We can remember that this is the equation y equals x minus 2. This is the equation y equals x minus 1. This is the equation y equals 0. This is the equation x equals 0. So let's just do the sides for a minute. Suppose, for example, you were going to worry about the equation y equals 0. Suppose I plug that in over here. Then I'd have 0 equals 1/2 of u minus v, multiplied by 2 maybe or something. 0 equals u minus v, or u equals v. So that's actually an easy thing to graph. So if we had the uv plane over here, uv, u equals v, is a line that just goes right through the origin. U equals v. All right, let's consider some of the sides. So let's go on a new page here. Let's worry about what happens if x equals 0. We'll take that equation. So we'd have 0 equals 1/2 of x plus y. I'm sorry. not x plus y, but u plus v, u plus v. And so then if 0 equals u plus v, so u equals negative v. That's another easy equation. That looks like this. U equals negative v, because this is the UV plane again. All right, so we have two more lines to worry about. Let's say we're going to worry about the line y equals x minus 2. So we can do that. Let's go to a new page. So we have y equals x minus 2. We have the original transformation. X equals a half of u plus v. Y equals a half of u minus v. So plug that stuff in. So you have a half of u minus v equals 1/2 of u plus v minus 2. Um, I may be tempted to multiply everything by 2. I'll have u minus v equals u plus v, and then I have minus 4. And what do you notice then? So you might notice, for example, that the u's cancel from both sides. You get negative 2v equals negative 4, so v equals 2. But that's another easy graph. That's just you go up to v equals 2 and you draw a horizontal line. Okay, very similar reasoning now. We'll consider this line y equals x minus 1. So y equals x minus 1 with the same transformations. So don't forget y is a half of u minus v. X is a half of u plus v minus 1. Multiply by 2 again. U minus v equals u plus v, this time minus 2. Cancel the u's. Negative 2v equals negative 2, so v equals 1. Okay, so we're ready now to describe our new region in the UV plane because we have 4 equations. We have the equation v equals 1. We have the equation v equals 2. We have the equation, let's fix that a little bit, sorry. It's got to go through the origin. U equals negative v, and we have the equation u equals, sorry about that, positive v. So you can see now that we've got a new trapezoidal region to consider. And now our limits of integration fall out pretty nicely. Earlier I decided to I wrote the integral this way and it turned out to be a good hunch. Double integral, I wrote e to the u over v times a half, and then I said let's do du dv. You can clearly tell here that u is varying between negative v and positive v. And that's going to happen as v varies between 1 and 2. So your outer limits are 1 to 2. Okay, so let's go to a new page and calculate all that. So here we go. 1/2 the double integral 1 to 2 negative v to positive v e to the u over v du dv. Okay, so we're trying to think of something that would have this thing as a derivative. Well, as a derivative. So the antiderivative, you know it has to have an e to the u over v in it. So is that the antiderivative? Well, if I did a little check temporarily, suppose I was going to check and see it, is this the antiderivative here? I would take the derivative of it, and I would get e to the same exponent times the derivative of the exponent, which would be 1 over v. So now I know that there must have been a v in front because that's the only thing that would have canceled this out when it came down. So this is my antiderivative there, v e to the u over v. So it's actually going to be pretty nice. So v e to the u over v evaluated from your limits of integration here, negative v to v. So negative v to v. Just don't forget, we did the antiderivative with respect to u. So we're plugging these little v's into this u that's up top here. So don't forget that. So we would get v e to the v over v minus v e to the v over negative v. Okay, so what happens there? It becomes v e to the 1 minus v e to the negative 1. If we want, we can factor out a v for our outside integral, which is going to go from 1 to 2. We would have an e to the 1 minus e to the negative 1 times v dv. Why not put that constant out in front there? So you'd have e minus 1 over e times the integral from 1 to 2 v dv. And we haven't seen an integral that easy in a long time, probably. So this little piece of it, just this part, we'll worry about. It's 1 half v squared, evaluated from 1 to 2. If I plug 2 in, so if I plug 2 in, I got a 4 times a half is a 2. Plug in 1 minus a half, so I'm getting a 1.5 or 3 halves times this thing. So this and this going to get multiplied. And let's not forget, I almost forgot that Jacobian up here. You probably noticed that, well, there it is right there, that Jacobian. I left it out in front. I brought it out, and I just got to remember to multiply by the answer at the end. So when everything's said and done, I end up with 1 half times that thing times that thing. So a half times 3 halves is 3/4. So 3/4 times e minus 1 over e. And there you have it. So that's a nice problem. Jacobian actually isn't so bad. It looks scary, but you realize you can move between things pretty nicely. Okay, thanks for watching.